Good afternoon. Before we start, I think we wait still 1 minute so that maybe some more can join. Okay, 1:15. Welcome to our second EDAX Symposium at the MC 2021. René de Clou is our EBSD and application specialist at EDAX, and he will show you in the next, close to an hour, a little bit more about advanced EBSD data processing based on our well-known OIM Analysis software. Enjoy the workshop or the symposium, and René, you can start.
Thank you very much, Michaela. Welcome, everybody. This presentation is on EBSD data processing, what you can do with the data, and maybe also a little bit what you should do with your data. So I'll be talking about selection, validation, quantification, some things to keep in mind when you are processing your EBSD results. So I have a quick introduction, then I will explain how OIM analysis works if you've never seen that before. A few words on data optimization. So how can you really improve your data, feature correlations, some new features, and finally, some big new functions that we have recently introduced in OIM Analysis 8.6. That is parent grain reconstruction, going to high temperature microstructures, and also OIM matrix, where we talk about dictionary indexing, dynamic simulations of EBSD patterns. So first of all, you need to consider, why do you use an EBSD system? When people are looking for systems, and the first questions we get when people want information is that people are looking at the data collection and detector hardware specifications. So these are easy numbers to talk about. How big is the chip? How fast can the camera go? Is the detector sensitive? How easy is it to use, etc. Of course, very, very important measures, but it's not all. So let's start with a few numbers about the EDAX EBSD detectors. First of all, here's our velocity series. We have 3 different models, different maximum speeds, 2,000, 3,000, 4,500 points per second, etc. Then we also have a DigiView series detector. It's extremely flexible. We can fit it to most SCM chambers, even ultra-high vacuum systems with copper gaskets, large chamber, very small chamber SCMs, different diameters of the sensor, etc. So it's very, very flexible. And of course, we had a presentation about this yesterday as well. The Clarity direct electron EBSD detector, no read noise, fantastic quality diffraction patterns for very sharp, high dynamic range imaging, and also extremely sensitive, that you can run at a few tenths of picoamp of beam current. But I don't really want to talk about that now, because this focus on the hardware really ignores why you are using an EBSD system. So what you really want to do is understand your material. So you need to get the quantitative data that helps you understand your materials, your samples, and resolve your analytical problems. So what do you need for that? Obviously, Data analysis is really important. And some of the features we have in OIM Analysis that are going to help you with this is full map, that's single button tools, but also subset selection. So specific areas on your sample or on your data set that you want to work with. Another very important feature, data validation. How are we certain that certain points are indexed correctly? Can we trust the data points? Once you've done your analysis, once you've set everything up and you have a repeated analysis, maybe tomorrow you have to do a similar sample and you don't want to redo everything, you can create templates and automate your analysis to save time. It's also very, very flexible. We have interactive analysis, and I will show you a little bit more about that later on. And here is just a little graphic of what kind of information we can extract from the EBSD datasets. We can make maps, of course. These are the colorful images that everybody is used to when we talk about EBSD data. But we can also quantify almost everything we can display in a map. Then we can create discrete plots, pole figures, inverse pole figures, Euler plots, etc. And we can quantify those in texture calculations. So this quantification is very important. It's not just about images. Now, this is what the OIM analysis software looks like. We have a number of toolbars, a project, and all the data that is displayed. So here's just the standard toolbar, a crystallographic calculator. This is a toolbar, just single button tools to create your analysis, interactive analysis highlighting toolbar. So all of the main functions are directly available from the user interface, and everything you've done is stored here in the project tree. And finally, once you've created some kind of analysis, the data is displayed in this very large area over here, where we can show maps, plots, charts, text windows, and in many cases also secondary view panes with the legend, but also interactive data and flexible displays of your map. Now, what is really important to remember in the analysis software is that everything we do is organized by what we call a partition. So we have, in my project, I have a data set, that's this black icon, and then we have a red icon, which is a subset or a partition. And everything we do in that partition only uses the data I have allowed in that subset. That is something that is crucial later on. So let's look at that in a little bit more detail. So when we have the project, all the documents, all the analysis, maps, plots, charts, everything you do are stored in this one file. And in the project, we can have multiple data sets. So in this case, they're indicated with these black icons. And inside each of these data sets, we can have partitions or subsets. And all data, there's not much of a filter or a subset, it's just everything. But here, for example, I have created a partition that only shows the small alpha grains. So ignore beta, ignore the larger grains, just a very specific part of your microstructure. And everything that I make underneath one of these partitions only uses the data that I allow in my partition. So you can make very dedicated maps and calculations for parts of your data set. Of course, you can also do charts, as I just mentioned, where we just quantify the displays, and also many things we can't display, we can still quantify. There's a large collection of charts available. We can also make textures, and you can even make multiple textures inside a single partition. So you can calculate a texture with different parameters, just what you need to do. And then inside a texture, you have the plots, ODF calculations, IPF, pole figure plots that belong to that particular calculation. So there's a lot of flexibility in here where you can really dedicate and tweak your analysis to your material. Then finally, here at the top, there are multi-charts, and that's a chart where we can actually combine and compare data from different partitions. Otherwise, when I make it in a partition, I would only use that data, but with a multi-chart, I can merge data from different data sets or different partitions. Now, this is the quick generate toolbar, as we call it. These are predefined maps. So for example, image quality map is just one click and you have the map of interest. There's an IPF map. This is a crystal direction map by default of the crystal direction sticking out of your sample, but of course you can change that as well. You can make charts, grain size, misorientation distribution, etc. just with one mouse click. If you want to make any changes, and this is the case everywhere in the software, there are contextual menus available. So if you want to make a change on a map or a chart, just right click on that location, you'll get a property window and you can select what you want to do. You can combine different types of maps, you can add boundaries, etc. And there's a large variation. In this case, I'm going to add an IPF map, and then we just superimpose those two types of maps. And if I want to, I can also add boundaries of different types and definitions. Now, once you've made such a special map, in this case, here is an IPF map on image quality with different boundaries. These are sigma 3, sigma 9 twin boundaries, so special misorientations. If you need this more than once, you can just create a map once, or a plot or a chart, and record it as a template. And you can make templates for maps, plots, charts, textures, so the individual displays, but you can also do that for a full analysis. So if you have made a partition with a subset and some kind of filter in that partition, you can make a template for that filter and all the analysis that you have made for that part of your data set. And you can also do dataset templates, and you can even do a batch processing with those. So once you've made your template of what you want to analyze, you can do a batch processing and just get a large number of datasets processed in exactly the same way with just a single mouse click. In this batch processor, we can also save all the images, the legends, so you don't have to save those individually anymore. It's all automatic. And an additional thing that may not be that well known is that everything we do, all the maps, plots, charts, you always have an option to export the original data. So if there is something that you want to do your own calculations on, or you want to import it into some other program, you can always access all the data. Now, these templates, if you have made a number of templates, there's a special place here where we can show them, we can put them in a map or in a folder, sorry. And you can just select from this pull down the different types of analysis you want to apply to your data set. If you have a few templates that you want to use more often, that you don't want to browse through a long list, you can actually program them directly into the user interface. These templates can then be used to batch process data sets. So you could apply a cleanup. You can define how you want to save all your images. If you want to do any other processing to your data, you can automatically export that for a whole sequence of data sets. And now, here's just an example why you would want to do template analysis here. So one thing, if you make a map, in this case, it's a grain size map. The color coding, the scaling of the map is always done with respect to the data inside your map. So here I have 3 data sets of a sample collected at different magnifications, different step sizes. And the color coding is always from minimum blue to maximum red. And here you would say, okay, yeah, I have this red everywhere. I have blue, green. So probably the range of grain sizes is very similar in these data sets. But that's not true, because this data set doesn't know that this one goes to 10 micron. So here, the red grains are only 3 micron, and here it's 10. So if you really want to be able to compare different data sets that you may have collected at different step sizes, different magnifications, you can make a template where you just set the minimum maximum value, and then you can really take an honest comparison between those data sets, and you can see what the real changes are. Okay, then the partitions. I already mentioned a few times that a partition is a subset of your data where you can do any kind of filtering. This is a screenshot of the partition properties dialog. You can select point properties. So what kind of properties does a point have to obey before we allow it in our subset? Or you can do it by grain. And you can define how we define a grain. That would be on the next tab here. So here you have a formula that you can make. And in this case, we have defined grain size in a certain way, all the grains smaller than 2.5 micron, and they have to be alpha titanium. So in this case, I have now a map where I just show those small alpha titanium grains and a pole figure that goes with it. And here I have the larger alpha titanium grains with the pole figure that goes with it. So with these partition formulas, you can very easily create sections of your data set that you want to analyze separately. A common way for partitioning that you normally don't even realize that's happening is the phase separation. If you have a multi-phase sample here, a material with austenite and ferrite, the phase separation or the partitioning is already done during mapping by the indexing. So the software recognizes which grains, which pixels are austenite and ferrite, and it will automatically assign the proper phases. But then in the analysis software, we can separate those two in individual maps. Here on the left is just the austenite phase. Here on the right in color is just the ferrite fraction that's left over. And then you can make a grain size chart. For example, here is everything, so austenite and ferrite, but you can split them. So the ferrite grains were the small ones, and the austenite grains, the green is the larger one, and in red is just a combination of both. And you can, of course, also characterize the interface between the two phases, between the two partitions that we have identified. So in this case, it gives you information about the austenite ferrite phase transformation that has occurred in this material. If it's not so easy to draw or to create a formula based on a fixed number somewhere in the partition properties, we can also do highlighting. So we can make a chart, and on that chart, you can just select a range of bars or points, and we can use that to split the different components in our data set. So in this case, I have here for grain orientation spread, the grains that have very little spread, so no deformation, that's the recrystallized fraction in this grain, in this sample. And the deformed fraction here on the right, that's the heavily deformed material with a lot of spread inside the grains. So this may not be always the same between different materials. So then you can use this interactive highlighting to pinpoint where the transition is. And of course, you can do then further analysis for each fraction. Now, if even that is not possible, you can also click directly in the map. So here I have an example of a gold film on a silicon substrate. And here on the right-hand side, in the previous image, we have good orientation contrast. We can see like a feather-like structure. And in the middle here, we have the IPF superimposed. Now, if I want to separate those large grains from the small grains, in this case, what I could do is just click in those large grains, and the software will just select the points that belong to them. And when I've done that, I can split them, and also for both do their own analysis. Now, obviously, on the large grains, you have very few boundaries. And for the smaller grains, you have lots of boundaries. But if you would scale those two charts, these are just the number of low angle boundaries that we have here, you can see that the distribution is the same. So that tells you something about the scaling of this microstructure. In OIM Analysis 8, already a few years ago, we have added a really new dimension to partitioning. That's when we record all the EBSD patterns, we can extract them, we can use bits of the data set to do new processing to the EBSD patterns and to really optimize the indexing results. So when we have a map here, I can just move my mouse over the data set and you can see the original pattern, orientation, the reconstructed pattern. But you can also extract individual patterns for different phases or for a different partition. And you can optimize the background processing for specific phases. And I have an example of that later on where it can be very useful. And one of the main reasons why you would want to do that is that if you have a mixed material with multiple phases where different phases have very different backscatter contrast, different intensity in the diffraction pattern, an overall background may not be ideal, and then we can really optimize for each material individually. Then finally, what we can also do is NPAR. This is a tool, it's just a checkbox here, where we do like a moving average of the diffraction patterns directly. So on the map, we go for each pixel, we take the 6 pixels around it, average those 7 points, and then index that pattern. And that is an extremely powerful tool to extract indexable patterns from very, very poor patterns or very noisy data sets. And just to illustrate that, here I have a sample with horrible curtaining from FIB milling. So something went a little bit wrong here. And when we do normal EBSD mapping, it's not a problem to get mapping information from the left, but from this curtained area, you get very little signal because of the shadowing. But when you average the patterns from the neighboring grains for each pixel, you are smoothing out that shadowing gradient, and you can actually get indexable data for the entire surface area. So it's like a curtain that is lifted here, and we can see everything underneath. Now, this is an example on curtaining from FIB milling, but you can imagine that you can also use this for fracture surfaces where you just cannot apply a polishing. So when you have an irregular surface that is producing diffraction patterns but causing trouble because of shadowing and different orientations of the surface, then applying NPAR to that will greatly improve the indexing success rates. Now, there may still be points that we cannot index. And here I have just a few examples. On the left, there's some misindexing, maybe along grain boundaries. In the middle, we may have missed a phase, and the black areas here may be something that we just couldn't index during the original indexing. Or here on the right, when we have a material with lots of pores. So what can we do about that? And the first thing we have to consider is how do we identify which points are reliable? So which points are really badly indexed, and how can we separate those from the good points? And we do that in our indexing algorithm, the triplet voting. What we do for each pattern is we look at all the diffraction bands that we want to work with. And in this example, I'm just using 5. So the magenta, yellow, blue, green, and red. And for each triangle, I'm going to see if there is an orientation that fits those 3 bands. Sometimes there's only one orientation. Sometimes there's more than one. But then we can make a table that says, okay, these are all my candidate orientations that I can make from one or more of those triplets. And these are all my triangles. In the end, we can see that the solution with the largest number of triplets is probably the correct solution. For each of those triplets, we have an orientation. So we have a little cloud of orientations, and then we can average those orientations. That's a little red cross you see here, and that's the orientation that is recorded in your data set. And one of the benefits for that is that for each pattern, we are typically calculating between 35 and or more than 100 individual orientations, depending on the triangles that we can get. And when you average those, even if there is a little bit of noise in the band detection, the averaging really improves the measurement precision, so that at any mapping speed and even with relatively poor diffraction patterns, you can get indexing precision between 0.1 and 0.3 degree. So the example I have here is in a deformed steel, and here I have made a profile, and you can see the orientation changes in the profile is typically between 0.1 and 0.2 degrees with a few spikes coming out. And these peaks are actually the true low angle boundaries that we have along the profile. Now, another advantage of the triplet voting is that we are not calculating one possible orientation. We know if there is a second one that is similar, maybe, or even identical with pseudosymmetry. So what you can do is you can check the difference between the solution with the best number of triangles and the second best. And we are using a parameter that we call the confidence index for that to really highlight how unique a certain solution is. And it is important because when you only use a fit angle parameter and you have two patterns, two solutions that would fit equally well in a pseudosymmetry situation, then the fit may tell you that all the bands match and the misfit is very small, so it's a perfect solution. It doesn't tell you if there's a second one. And also, if you have overlapping patterns at a grain boundary, the fit is not going to help you when you are going to have a number of bands that are coming from a second orientation. But the triplets can be, let's say, identified for the individual grains. We can see what the best solution is with the largest number of triangles and what the second best solution is. And based on that, we can calculate the confidence index. For this example, it's the CI is 10 minus 4 divided by the maximum number of votes or triplets it could have found is 0.6. Now, when the best solution has there's 10% more triplets than the second best, it's typically correct. And that's a threshold that we typically use for the confidence index larger than 0.1. And that's something that we use afterwards to filter out not necessarily bad indexing only, but also suspicious indexing that may not be obvious at first glance. So just to illustrate that, here I have a data set. It's a zinc aluminium alloy where not all the patterns were great. We can see there's some noise in there. And when I apply a CI filter, then I get about 75% correctly indexed and the bad points all drop out and they show white. I can then invert that filter and I can only use the bad points. I can only show those. Then I go to my reindexing. I can do any processing to the pattern that I want to, and I only modify the points that were misindexed in the first place. And when I do that, in this case, I can get the indexing success rate up to almost 97%. And I also identified a second phase in here, actually, that is here indicated in the middle map. So this way, you just keep the good points that we measured directly. Afterwards, we can tweak and then really optimize the band detection and the pattern appearance, and then really maximize the indexing result for your analysis. We can also add missing phases. In this case, I had an iron silicide material with a number of phases. There were 8, but not all 8 in this small phase, this small data set. And there was one phase that I didn't recognize initially, so it's indicated in these circles. There's just noisy points there. And then we can separate those points out either by confidence index or maybe by the chemistry. And then we just have a partition or a subset with just all these bad points. Then I can get a pattern from there, optimize that with a number of image processing tools that I want to apply, and I can identify what the phase is. And then I can reindex only those points, so don't touch anything else. And then we have a really nice addition to our multi-phase sample. And this way you can just maximize your indexing results. Now, here's another one. At first glance, it looked like these black areas were just dirt on the sample because they didn't give any patterns, maybe some contamination. But when we look more carefully, number 1 and number 2, you can just make out something. There's a hint of a pattern in there. And when I extract those points and really maximize the image processing there, I can extract actually patterns that look like this. And that is very indexable. So now also for here, I could just take just those points, reindex them, in this case with a tetragonal tungsten molybdenum phase, and add those into the original data set. Now, if you have a multi-phase sample, you can of course also use chemical information if you want to separate materials. And you can, it's very useful if you have phases that are almost identical crystallographically. For example, copper and nickel or austenite, then the patterns are almost impossible to distinguish just based on the crystal structure. But with the chemistry, that's easy. Also, if you have a multi-phase sample, and this is one that may not be so obvious at first, when you polish a material, the polishing is not the same for all phases. Typically, you're trying to optimize the polish for the matrix, for the largest volume fraction of your sample, but some other phases may not polish so nicely. And then you have very good and very poor patterns, and that can also easily cause misindexing. And you can also use EDS to separate out some of those poorly indexed phases, and as I've just shown, maximize that. So here is just going back. This is this area after really adding all 8 phases. This was done using chemistry as well. Now, there is an issue when you're looking at chemistry, and that is that the interaction volume of an EDS analysis is much bigger than for EBSD. Under typical EBSD conditions, let's say 20 kV, a few nanoamp, you easily have a 1 micron interaction volume for EDS, where the EBSD data is coming from 20 by 20 by 20 nanometer perhaps. So if you have a sample like here, where I have a metal matrix with carbides, the carbides can easily be identified in the EDS map. But when we zoom in, you can also see that the chemical signal does not match the grains. The chemical signal is bigger than where the grains are. And that will cause some trouble when you are using the chemistry to separate 2 phases. So if I do that here, using this EDS information, you can see that I get double boundaries here. And that's just the shadow, the overlapping of the chemical signal between the carbide and the matrix. What I can do in the analysis software is, once I have good indexing everywhere, and if the crystal structures are the same, you will get good indexing also from those carbides. You can actually average the chemical signal by grain. And that means that you can get really sharp boundaries between the particles and the matrix. Now, that was one reindexing example. Now, another thing is where we cannot do reindexing. When we have misindexed points, but basically caused by porosity. So when there is nothing there. What we can do there is we can group those misindexed pixels that were not crystalline and group them together as anti-grains. So when I do that, I can just get these clusters of points that belong to those black areas, and I can actually analyze those as if they were grains. So I can do a full porosity analysis where I can look at the grain size, grain shape, circumference, elongation analysis, etc., as if these were complete grains. So this can be very useful, for example, when you have 3D printed materials where you have sometimes a significant porosity, and you can just characterize that very nicely. And here I just do a highlighting where the smallest ones are blue, the largest ones are in red, and you can see the distribution a bit more clearly. And once I have that, as I just mentioned, you can do all kind of geometrical analysis. In here I have the aspect ratio, so that's the elongation of the pores, also color coded, and of course it's all quantified. Now, the next thing, feature correlation. When you have EBSD, one of the strong points of EBSD is that we know exactly where each measurement comes from. So it's not a bulk measurement that is averaged on a sensor, it's really localized, which means that we can correlate the different features between plots and maps and charts, etc. And this correlation, this direct access to this data that allows you this correlation, we can really do a special data manipulation and subset generation. So just an example for that. Here I have my partially recrystallized steel again, and here I have my pole figures, inverse pole figure, and you can see are these little black clusters. These are for the recrystallized grains, but when you have these darker areas here, there are so many pixels from the deformed grains, you cannot see what is happening in there from these black clusters. So what you can do is you can color code the map, in this case orientation spread, which allows us to see the recrystallized and the deformed grains, and then you can apply that color coding to the pole figures. So I just right click, as I mentioned earlier, if you want to make any changes, just right click, apply color as highlight, and when we do that, then these pole figures are now shown in the same color coding as the map, and you can very quickly correlate the distribution of the different grains in there. This highlighting works with any color coding that you can make. And another one, here I have laser crystallized silicon germanium film. There is some elongation in here along these bars that we can see. And the question is there a specific orientation or crystal direction parallel to this grain elongation? So is there a preferred crystallization direction when it's hit by the laser? So what you can do for that is first you need to identify the shape of those grains. So here we can make best fit ellipses to the entire grains. And for each of these ellipses, we can identify the crystal direction parallel to the longest axis of that ellipse. Now, there's a big note here. It's in the plane of the sample. So it's extremely important that you have your sectioning correct. Otherwise, we don't know what is happening in the third dimension. But once we've done that, we can color code all the grains individually by the longest axis of the grain. So it's not parallel to one fixed external axis, but each grain has its own reference axis as indicated by these ellipses. And you can see that most of the grains are red, indicating that it's the 001 is the preferred crystallization direction. You can also quantify this grain shape orientation in a different way. Here I have a color coding for the shape orientation. And this is just in angles, so 8 degrees and 280 degrees left to right. And you can see that here in that distribution. We can highlight those with a more logical, perhaps, color coding, where horizontal is blue and vertical is red. So you can a little bit clearer picture. And we can also quantify that in a different type of plot. So you can nicely see the distribution of these orientations. A new feature that we have introduced recently in the software is correlative plots. And just to illustrate what I mean by that is that almost everything we can show in color, we can quantify in a chart. And also all the numbers are available if you want to do that. So there's the grain aspect ratio. So that's the elongation. But I can also do the grain size. So there's my grain size map. And if I now want to know if my grain size and elongation is correlated in any way, I can just create a correlative plot where I can just put these against each other. You could, of course, always do this already in an external program where you just export the data for each individual parameter, but it's much more easy now to do this directly in the analysis software. If there are still things you want to do that you cannot find in the software, you can ask us. In many cases, there are lots of functions in there that you may not have found yet. Just feel free to ask. But if there is something that we have not implemented in the software, you can export everything. So you can export the data, boundaries, reconstructed boundaries, as we see here, they're vectorized, triple points, and grain file, lots of information, because all the raw data is available. And here's just an example. This is an EBSD map of aluminium kitchen foil. That's a beautiful demonstration sample. If you need something nice, just put the shiny side in the microscope. It gives nice patterns. We have the grain size distribution. And if you look at the export grain file, you see a lot of parameters that you can export. And in this example, I just want to illustrate the number of neighbors of each grain. So how many grains are surrounding each grain in general. So when you get a text file like that, you get a little header that explains exactly what each column is. And then you can quantify that and process it further in an external program. Now, the last few slides, there's a new features we put in the software. And one is the parent grain reconstruction, where when you start at high temperature material during processing or forming, you may have one phase. When you cool it down, you may get a phase transformation where that grain breaks apart in lots of different orientations. And if you want to understand the processes happening at high temperature, it's very helpful to know the microstructure under these conditions. And this tool will help you to reconstruct that. And the other one, OIM Matrix, is a special software package where we use dynamic simulations of EBSD patterns to do dictionary indexing, where we can really look at details in patterns, polarity determination, for examples, but also it allows a tool for diffraction in general, crystallographic information, also especially in combination with the Clarity direct electron detector. Now, just as an example, I have here a heating stage experiment with cobalt. And cobalt has a phase transformation around 422 degrees, where at high temperature you have a cubic phase, and at low temperature you have an hexagonal phase. And in this case, we did a number of experiments where we just heat the sample. It transforms from the low temperature to the high temperature phase, cool it down, it transforms back to a hexagonal phase, and heat it up again, it goes back to the cubic phase. This is a perfect example to verify if the parent grain reconstruction actually works. Because at ambient temperature, where we have mainly the hexagonal structure and a little bit of the cubic structure, when we go to high temperature, it transforms into the cubic structure with a few alpha grains left over. So when we do the parent grain reconstruction, we can start with this map on the top left, the ambient temperature map, reconstruct the data there, and here on the right, you can see the result. So that's the reconstruction. And if you compare that with the actual measured map here on the lower left, you can see that they are very, very similar. So there may be a few small variations in twin locations and low angle boundaries, but the overall grain shape, grain size, misorientation distribution is very valid. You can also do that for steels. Here I have a martensitic steel. You can see all the different lamellae. You can just make out the overall shape of the original high temperature austenite grains, and we can reconstruct that. There's a number of models available to do so, and you can see which ones here work best. And in this material, it's this one, the Nishiyama Wasserman in the top center, that really shows a good microstructure. You can also look at the pole figures, and here you start to see this is just noise. Effectively, there's no orientation, and here we have a little bit more structure in the pole figures. Then dynamic pattern simulations for dictionary indexing and comparison of different patterns. Here we can take, in this case, about 2 billion electrons. We put them in the structure, let them diffract according to dynamic theory, and that will give us a master pattern. So we can just calculate and define the diffracted intensity all around the crystal in a sphere. Then we can just modify that into a flat display by a projection, but of course it's a three-dimensional structure. And then based on that, you can specify with your own detector geometry, the actual sample tilt, etc., what the diffraction pattern is supposed to look like. So then you can compare, in the case of pseudosymmetry or polarity, you create the 2 or 3 different equivalent simulations, and you can see which one fits best with your experimental pattern. We can also use that for dictionary indexing. Now, in this slide, we show nice quality patterns. In general, they're not so nice, but here we have an experimental pattern on the left. We create a dictionary where we have a whole folder full of all possible orientations with a given angular interval between them, and then we can check which of these simulated patterns matches the experimental pattern best. Now, on a good pattern, that's relatively easy. When you have extremely poor patterns, it actually works much better than you might think. So even very noisy patterns with this tool can be made to fit a nice simulated diffraction pattern. And just to illustrate that, I have here a very highly deformed compressed ferrite sample. So very fine grains. You can see the scale bar, image quality map where it's black. The patterns are very, very poor. And the indexing here on the right is actually not too bad. We have a lot of grains visible, also a lot of noise. So when I apply a CI filter, so confidence index below 0.1, I hide, then we can see that the indexing success rate is around 50%. When I apply dictionary indexing to this exact data set, I get this. So the image quality map looks different because it's based on the Huff transform, which we don't have for the dictionary indexing. It's a different algorithm. But if you look here at the IPF map, you can see that the noise areas are much, much smaller, and we have a really nice coverage of properly indexed grains. And when I remove the noise here, we are over 82% indexed when compared to the 50% that we had before. So it's a very, very sensitive tool for very poor quality patterns to improve the indexing result. So this is also one of the latest additions to the OIM analysis software. So just to summarize that, it's an extremely powerful tool to investigate your materials, visualize them, quantify them, everything based on the crystal orientations. A lot of the basic functions are just directly available by single mouse clicks, but there is much more below the surface. There's many more analysis functions, comparative functions, interactive analysis that you can do. You can make your templates, you can make your own one-button tools, and all the different displays, maps, plots, charts are linked to their original measurement point, and you can correlate them and really work at understanding your materials. And then one of the biggest changes in the last few years actually is the reindexing with the pattern processing with NPAR based on the partitions to really maximize indexing success rates. And the recent introduction of this parent grain reconstruction, OIM matrix dictionary indexing really helps further the capabilities of the software. Okay, so these were a lot of slides. I want to quickly show you how you can work with the software, and just for a few minutes, and then we can have if you have any questions, just let me know. So let me switch to the software. So here we have OIM analysis. I've shown the toolbars, the area of analysis. So let me just load a data set, and which one shall we take? I'll just take this one. It's a little bit blurry, but it's a nice one to work with porosity, for example. So here I just load the data set. We get the data set. I get my partition. I get my maps just by clicking here in the toolbar. If I want to see the grain boundaries, that's another button that I have here. So you can quantify the grain boundaries in one go. I don't care about that too much right now. And I can do a grain size analysis or a misorientation distribution analysis. And here we have, for example, very clearly a large peak in the misorientation chart. If I want to see where those points are, I can just click them. And the software will show you, in this case, it's around all the twins that we have here in the software. If I want to see the grain size distribution, I can just drag a box over this chart and the map will be color coded from blue to red, or any other color scheme that I can define. So these are the actual grains. If I'm interested in a porosity, I can just go to the grain size, right click, properties, and here I can change what I want to do. I can change the range, the size, the display of the chart, but also the grain mode. So here I go from grain to anti-grain. And when I now highlight that, these are my pores. So with this, I have identified my pore locations, and then I can also create maps and charts for, as I've shown, for the elongation, the grain shape, etc. Another one I would like to display is this one. So here, again, I just start with these two main buttons. And here there is one grain that for some reason shows some indexing problems. So let's see if we can improve that. What I can do now, I can just select an area around that grain, right click, send to partition. So I now made a new subset of that grain and the direct surroundings. Then I can in FlexiView, I can show the orientations, I can show the patterns and everything there, and I can just click in here and reindex that. I can modify the Huff transformation if I want to. I can add or change the phase assignment if I want to. I can change image processing. So I can do NPAR on that. It's not necessary. These patterns are already great, but you can modify that. And here I can say, save in a new file. Yeah, don't change my original one. And an important one, don't change the gray level maps in the background like IQ, because then only this area would look different from everything else. So when I do that, reindex, and it very quickly just goes over the map and only changes that grain, that area. And as you can see now, this looks nice. And we have a data set that we can work with. So there's the phase map. And we can, if I make a new map here, image quality with IPF, you can see how you can add grains. Let's make that in a black color. So now let's add the boundaries to that. And once you've made one of those, right click, you can make a template, but you can also just copy it and paste it into the subsets for ferrite and austenite. So it's a very intuitive interface. Effectively, when you know how to make one map, you know how to make them all. So, and with that, I would like to conclude and ask if you have any questions.
Thanks, René, for this nice and informative presentation. I see so far that Markus Kübach has a question.
Yes, please.
Yeah.
Hello. Yeah. Thank you. Can you hear me?
Yes, I can hear you.
Perfect.
Thank you.
Thank you very much. Thank you very much for this talk. It's really fascinating to see what you can now do also within this software. What I remember back a couple of years ago was still possible with kind of MTeX hacking and scripting. So that's certainly added on making these tools more accessible to users who are familiar with GUIs. My question would be, so you have shown also the export functionalities of the software, but how is it essentially then with the metadata tracking that you have implemented in the software? So does the software internally keep a state of the individual actions that you take, so to say that you can not only export figures, because they normally are then taken over in other publications and usually further modified by the scientists, but how can you then also supplement these figures with metadata, so ideally the entire state from the software that brought you to these results, so that these things become more reproducible? I know there's templating, but this is in fact here a different level of reproducibility that I'm aiming for.
Yeah.
So what is the strategy towards this?
If you, and in general, we never change the original data set. So the moment we open it into OIM Analysis, it becomes a project, and everything we do is recorded in the project, and we don't do anything with the original data set.
Yeah, so memory mapped. Okay.
Yeah, so that is separated. Then any rotation, cleanup, or whatever other function you might do gets logged in the data set and in the partition. It will have a little summary view that shows exactly what filters were applied and what operations were applied to the entire data set. So that is available in there.
That is definitely super useful. So what would you then recommend for scientists when they deliver supplementary data for their publications? And normally they usually give only a short method description and then maybe the final figure that they created. But what should people then export as additional supplementary material? Is there, for instance, then a very specifically formatted output file that people can submit along with their publication, or what is offered, so to say, to support the scientists on this side?
Well, you can export a text file with the data, but in general, what I would really like to see in publications is what the user has done.
Exactly.
I want to see, I want to
Yeah.
know if they've done any cleanup, and if so, how many % of the data set has been cleaned? Because I see by your reaction, you've seen that. When I think EBSD is the only technique in the scientific community where users are allowed to invent a large part of their own data and nobody complains.
Honestly, I was grown up at a time when it was still common that people performed grain growth with Kubehara filter in software, you know. So, and that I think still hasn't maybe changed because the tools are so intuitive. And then people obviously are now able to make all these nice modifications at their fingertips. But the downside is, of course, then you get a highly processed image where it then really depends totally on the scientist, what you report in a high impact paper, and how this contributes to the story. And I think this is a little bit in short, maybe too short-minded view. So is there any activity or any support?
I fully agree with what you say. What I just mentioned, the cleaning, fraction of points changed, etc., that's all logged in the data set. So once you've done that, you can just export that as a text file and you have access to all these numbers. But yeah, you have to be careful. That's also why I personally like this reindexing tool so much. Since we have that, I can really target badly indexed areas, try to improve that. And I hardly ever use any other cleanup nowadays. I just do a little bit of cleanup when I do a parent grain reconstruction, because then I want the grains to touch each other. But otherwise, I just hide the bad points and work with what I've got.
Yeah, great. Thank you.
Okay, any other questions? And when there are no more questions, if you have any questions, please visit our booth. You can chat also with me. You can just send me a message and I will try to respond to you as soon as I can with any requests that you may have. But then I would like to thank you very much for your attention and enjoy the rest of the conference.